Inside a quiet hay shed, there are no engines running and no electrical faults in the wiring. The air is still, and there hasn't been a lightning strike in weeks. Yet, without any spark, thick white smoke slowly begins to seep from the deep crevices of the stacked hay. In a standard fire triangle, hay provides fuel and air provides oxygen. But here, the third side, heat, is pulsing from an unknown source. Without a match or cigarette, where is the energy coming from to ignite this massive pile of grass? Well, water is what we use to put fires out. Storing hay with excess internal moisture creates the conditions required for heat to build. The fire is the culmination of an invisible, escalating chain reaction driven by moisture trapped deep inside the bale. To find the source of that heat, we have to look at the microscopic level, deep inside a damp pile of forage. The cells of freshly cut plants continue to respire, while natural microbes living on the hay multiply in the trapped moisture. These microbes metabolize the organic matter, off-gassing carbon dioxide, water, and heat. A single microbe generates a negligible amount of thermal energy, but when thousands of bales are packed into dense piles, that heat begins to accumulate. This microbial community acts as a biological engine, transforming a damp bale of grass into an active heat generator. Under normal conditions, this biologically generated heat would move through the stack and cool off into the barn air. The internal temperature of the stack is governed by the balance of heat generated versus heat lost. When the physical density of the bale restricts airflow, the heat generated side tips the scale. The internal temperature climbs because the energy has nowhere to go. Large, tightly compressed bales have a low surface area to volume ratio. This means the heat generated in the middle has a long path to travel before it can escape. This creates a deceptive exterior. An operator can touch the outside of the stack and find it cool, while the deep center reaches dangerous temperatures. The physical structure of the bale serves as a thermal insulator, trapping the microbes' heat inside the stack. There is a common idea that bacteria keep heating the hay until it finally bursts into flames. But biological activity has a limit. As the temperature reaches extreme highs, the environment becomes too harsh, and the heat-generating microbes die off. At this point, the process shifts. As the biology dies, chemical oxidation takes over and begins generating its own heat. This creates a positive feedback loop. Chemical oxidation generates heat, which accelerates the oxidation rate, which produces even more heat. Once this runaway reaction crosses the ignition threshold, the material will spontaneously combust without an external flame. The final fire is a volatile chemical event, but it requires that initial biological primer to reach the starting temperature. A fire is the worst-case scenario, but the self-heating process causes economic damage long before a flame appears. Microbial metabolism consumes the dry matter and the stored energy of the forage. When the heat bakes the hay, it can turn brown and develop a sweet, caramel-like smell that appears appetizing for livestock. But this browning indicates a Maillard reaction, where proteins become bound with sugars. This leaves the nutrients heat-damaged and useless to the animals. Biological heating destroys the value of the inventory from the inside out, turning premium feed into a loss. Prevention begins before storage by properly drying the crop and verifying moisture levels during baling. Once the hay is stacked, recording the temperature turned over multiple days is more informative than a single isolated reading. If a haystack is discovered to be dangerously hot or actively smoking, do not attempt to pull the bales apart to find the hot spot. Dismantling the stack introduces a sudden rush of fresh oxygen to a smoldering chemical reaction, which can trigger an instant fireball. A smoking stack is an emergency that requires professional responders. Spontaneous combustion is the result of biology, physics, and chemistry left unchecked in the dark, a process that can be managed if moisture is controlled from the start.